Each day from 7 a.m. to 4 p.m., around 1,200 students go to Juniper Poplar Dining Hall. On average, each student wastes 8 ounces of food, amounting to 108 tons of food being thrown away each year. What can we do with the surplus of waste? It can be utilized for electricity generation by capturing and burning methane produced through the process of anaerobic digestion. That's where the electricity-generating compartmentalized biodigester comes into play. It is a reactor which will harvest biogas from dining hall food waste and transform the gas into usable energy. In order to make this project more manageable and easier to validate testing, we broke the project into 4 phases.
This project had to pass the following test requirements. An airtight biodigester had to be designed. The digester had to be kept in optimal conditions to produce biogas. An active monitoring system on a PCB was to be developed. And finally, an LED was to be lit using thermoelectric technology. The first problem we encountered while working on this project was ensuring safety for users. The biodigester was designed to be kept within permissible air exposure limits and at low pressure. An oxygen-free environment is essential for anaerobic digestion and to prohibit the digester from entering the upper explosion limit and lower explosion limit shown in the figure. To make the digester airtight, threaded rods were used to bolt the upper and lower panels to the main cylinder of the digester. Silicon caulk was used to seal any gaps between the polycarbonate materials where the panels are connected to the cylinder. Airtight food input, digestate output, and gas release valves were incorporated into the design. The reactor was designed with a 3 psi release valve, making the system low pressure, decreasing the risk of explosion. To aid in the biological factors of breakdown, the digester was kept outside as the optimal temperature is around 96 degrees Fahrenheit for decomposition. Food waste was grinded before being added to the digester. Each week more food was added so digestion would continue regularly.
A monitoring system was embedded internally in the biodigester, allowing system metrics to be seen. After milling the PCB design and soldering on the chosen circuit elements, the DHT22 and MQ4 sensors both function as seen here. The MQ4 sensor detects methane, combined with an LED, for visual confirmation when the gas is detected. The DHT22 sensor converts temperature and humidity levels to an analog voltage that the microcontroller can process. These readings are then displayed on an LCD. The system runs off a 9-volt source. A voltage regulator ensures the microcontroller and sensors are receiving a constant 5 volts. The Atmega 328P microcontroller was implemented on a standalone PCB by using a 16 MHz oscillator and other standard circuitry. A power switch and hardware reset were included to make testing more efficient. The PCB was designed and milled to include these systems.
For the final phase, an LED was illuminated by burning biogas onto a Peltier. When exposed to a persistent temperature differential, the Peltier produces current. Methane burns at a temperature of 2000 degrees Celsius. However, a Peltier can only handle around 200 degrees Celsius. Therefore, an aluminum plate had to be placed on the heated side of the Peltier for protection. To maintain the temperature differential, a heat sink, in this case an aluminum cube filled with water, was placed on the opposite side of the Peltier. This allowed the highest temperature potential without overheating the Peltier. In order to light the LED, 2 Peltiers were used in series to achieve a voltage of 1.8 volts. The electricity-generating compartmentalized biodigester safely produces methane while monitoring internal conditions. Burning this gas allowed usable energy to be generated while promoting green practices and economic efficiency.